So we finally switched gears away from a mathematical description of chemistry to more of a phenomenological description of chemistry. We've been talking about bonds all semester, and so we're going to get into how those bonds might form, how we might break those bonds, what the structure of molecules look like. But before we get there, right, in this more descriptive part of the course, we have to kind of start off with understanding that electron behavior is kind of strange, okay? And essentially, we have this situation where we are big objects and we follow what is known as classical mechanics. And there's a set of physics called quantum mechanics that describes how small things behave. And classical mechanics, like how we behave, and quantum mechanics, how small things behave, they're completely different. And so it's hard for us as big things that live in this big world and see how big things behave to understand how small things behave. But quantum mechanics is what allows us to do that. And in fact, we know that electrons are kind of weird just from the beginning of the semester, like especially if you think about looking at that covalent bond formation. Sometimes electrons are exchanged and get an ionic bond, but then there's sometimes this real complicated sharing that occurs. Electron behavior needs to be understood before we get to bonding. And because electrons behave in that strange way, we really need to just get a rudimentary understanding of quantum mechanics down and then see how that impacts electron behavior. See how that's important for us as chemists or people studying chemistry. So, what is quantum mechanics? Again, I mentioned it before, but it's the physics of small things. Okay, so small molecules and down. So, small molecules, atoms, definitely things inside an atom like electron, they all behave quantum mechanics. And you see some stuff that doesn't make sense to us in an intuitive way, okay, because we're big, okay. And the main thing with quantum mechanics that kind of doesn't mesh with how we view things is that only certain things are allowed and all others are forbidden. Now I put things in quotation marks because that's going to be certain types of physical properties, okay? And quantum mechanics is usually based off of making arguments about energy. Only certain energies are allowed and all others are forbidden, right? But then there's also some other things that we run into that are quantized. And whenever you hear that word quantized, it means allowed, right? Allowed, and others are forbidden, right? So there's only certain areas in the atom that are allowed for the electron, and all others are forbidden. There's only certain orientations of the electron that are allowed in an atom, and all others are forbidden. So it's just kind of like a general statement that just describes the general idea of quantum mechanics. Things are allowed, right, and all other ones are forbidden. When something's allowed, it gets what's known as a quantum number, right, a quantum number. And that just describes, all right, the list of things that are allowed. And if you're not on that list, then you'll never, ever, ever have that value. If you're not on that list, you're forbidden, right? And you never, ever observe it from an experimental standpoint. So the example that I'm going to give down here is a quantum car, okay? So we understand that if this was like our car, which our car is big, okay? So it definitely follows classical mechanics. So things are going to make sense. If we start at 0 miles per hour and we put our foot on the gas pedal, we're going to give our car kinetic energy, okay? So there's an engine inside that there's a combustion that occurs. We convert that energy into kinetic energy, okay? Now, what we'll see with this is like an old school speedometer, okay, where there would be like a needle here. What we would see is if we press on the gas pedal, this needle would like sweep out this whole range here. So say we wanted to hit 30 miles per hour. Well, what would you see? The needle would sort of go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and it'll go all the way up to 30 in a smooth way, right? It will just kind of go up and sweep out all of those different miles per hour, all those different velocities, and thus all those different kinetic energies. So you're saying, well, okay, that's great. Like, that kind of makes sense to us. But that's kind of the point. When something's big and we look at the behavior of big things, we can use our intuition. We can say, oh, yeah, that makes sense. I've seen that before. And we can't do that same thing with quantum mechanics. So let's say now that we had a quantum car. Now that we remember how a car works. Not that we forgot, but you get my point here. Let's say we had a quantum car. And let's say that only 10 miles per hour, 20 miles per hour, and 30 miles per hour were allowed past 0 miles per hour. Okay? then what you would do is you would press down on the gas pedal and nothing would happen. And you would keep pressing down on the gas pedal until you would have reached 10 miles per hour. And then instantaneously, you wouldn't even see it anywhere in between here. Instantaneously, this needle that was here would jump magically to 10 miles per hour. You would never ever see it in between, but in one instance, you would be going 0 miles per hour. And then in the next instance, you would be going 10 miles per hour. You would never be in between, okay? Because everything between 0 and 10 is forbidden because it doesn't have a quantum number associated with it, okay? So then you would keep going. You would push down on the pedal more. And guess what? Even if you're pushing down on the pedal more, you stay at 10 miles per hour. And then you push down on the pedal again and again and again, and eventually you would have put in enough energy to get to 20, and then you don't even see the needle moving in between 10 and 20. The needle automatically jumps to 20. You were never 15 miles an hour. You were never 19 miles an hour. In one instance, you were 10 miles an hour, and then you put in enough energy into the system, and then instantly you were 20 miles per hour, right? Never, ever anything in between. So you might be saying to yourself, well, that doesn't make sense, and I don't understand how that could possibly be the case. And that's actually good. That's the correct sort of response to have to this situation. Because quantum mechanics is how small things behave, all right? And so we don't have a physical intuition with or a real world experience that links us to their behavior. And so what we have to do is we have to trust the rules for what's allowed. We have to trust what we see experimentally, all right? And we have to realize that there's going to be some strange things that we run into, but then we just say, okay, yeah, that's just quantum mechanics. That's just how small things behave. And even if it doesn't sort of make physical, intuitive sense, right, we just kind of roll with it. Okay. So for electrons, what we have to learn is we have to learn about what's quantized, right, what the quantum numbers are, right, what the rules for those quantum numbers are, and then how eventually, probably next video, we'll look at how those quantum number rules actually give us the periodic table. Okay, so the next section is going to be the quantum numbers for electrons. And there's a set of 4. Okay, so there's 4 total descriptors that we need to describe electron behavior and start to think about why the periodic table is set up the way it is, and then eventually get on to, bonding and things like that in more advanced topics. Okay. So the first quantum number that we have is small n, right? And small n is known as the principal quantum number. Right? Q number is quantum number, so it's the principal quantum number. The information inside n is the electron's energy. So that's what it tells us. So that tells us that energy, just like our last example, the energy of an electron is quantized. Some electrons are allowed, some energies are allowed, other energies are forbidden. Okay. So what are the list of allowed n's? Okay. And every quantum number has a different list because there's a lot of math that happens in the background and we're just looking at the results of it. So what we have to do is just be really good about memorizing, all right, for a given quantum number, what the allowed values are. N can be 1, N can be 2, N can be 3, N can be 4. N can be any integer up to infinity. But notice, can N be 0? Nope. Can N be negative? No. Can N be 1.5? No. Can it be 2.39425? Nope. It can only be 1, 2, 3, or 4, right? And then on up from there, but nothing in between, okay? So what we do is we kind of build what are known as energy level diagrams from this idea, okay? And you may have seen this before, but I just want to show it to you. What we'll do here is we'll draw energy as an up axis, as like a y-axis. And then what we'll do is we'll say, okay, there's certain energy levels. Like here is the n equals 1 energy level, right? It's the lowest n, so it's the lowest energy, and we kind of write it down to the bottom of this arrow, right? The n equals 2 energy level then is going to be somewhere above that. It's a higher quantum number, so it's a higher energy. Okay. So electrons, they can be here, right? And they can occupy this state and they can have this energy. And then they can magically bump up here, right? But just like our quantum car, you can never be this range of energies in between. You can only be this energy, or n equals 3, 4, 5. But you know what I mean? It just kind of goes back to that quantum car. This is allowed, this is allowed. Nothing in between or anywhere else, right, is allowed. Everything else is forbidden. Okay? So principal quantum number gives energy. There's a set of allowed energies. They're described by the quantum number small n, which can only have integer values, positive integer values, all the way up to infinity. Now, once you know n, that gives us information about the next quantum number. And the next quantum number is cursive small l. Right, cursive small l. Now, this is known as the angular momentum quantum number. Right, the angular momentum quantum number. But I don't really want to get into a discussion of angular momentum because it's too much of an advanced topic for this course. So what are the practical implications of angular momentum, whatever that is, of angular momentum being quantized, of angular momentum being allowed and forbidden? What L gives us in terms of information is it gives us what's known as the electron's orbital. It gives the shape of the orbital, right? So what this means is it tells us where the electron lives. Right? And it doesn't actually exist in orbits, even though we use this word orbital. It's not like planets and the solar system, okay? Where the electron lives is sort of more complicated than that. But L tells us that, okay? So L can have certain values because there's only certain spots around the nucleus where the electron can live. L can have values of 0, 1, 2, okay. So it's a little bit different than n, and L equals 0 is allowed. But the main issue with L is the maximum value it can have is n minus 1. So what this notation means is you start at 0 and you count up by integer values until you get to n minus 1. Okay? So for example, and like I said before, like at the very beginning of this section, you have to be given an n to figure out what L's are allowed. So let's say we had an n equals 3. What this rule tells me is I can have an L of 0, 1, and 2. Now, why did I stop counting at 2, right? Because if I take a 3 here, what's 3 minus 1? It's 2. That reads as the maximum value of L that's allowed, right? So if I change this to n equals 2, what values of L are allowed? Well, 0's allowed, okay? 1's allowed. Is 2 allowed? No, it's outside the range of being allowed. So when n equals 2, L equals 0 or 1, right? There's only 2 allowed values of L. So now you can see what I mean. Like, you have to be given an n. The information in L depends on n, and you kind of go from there. Just as another extreme example, you probably won't see such a big n, but just to make sure you understand the rules, could really give you any n, right? But what about an n equals 5, right? Always start at 0 and then count from there. N minus 1 is 4, so I'm going to go 0, 1, 2, 3, 4. And those are the allowed L's for that particular n. So again, lots of math happening in background, but we understand that we just need to deal with the rule and be able to apply it, okay? So what about these orbital shapes? What about where the electron lives? So that's different too. Well, yeah, like you and me, we could walk anywhere we want on the Earth, right? As long as there's land underneath our feet. But for an electron, it's not the same, right? And in fact, when you have particular L's, you have particular regions where you're allowed to live. So when we have L equals 0, we call that an s orbital. And you'll see that you need to know this connection. L equals 0 corresponds to an s. That's an s every single time, right? An s orbital. Let me just make that real clear. S orbital. Okay. And if you look at your slideshow, which is labeled slideshow 6, 7, okay? If you look at slideshow 3, you'll see many pictures that describe an s orbital, right? But what you want to focus in on is the general shape that you see. And when L equals 0, what that tells us is, right, if the nucleus is somewhere in the middle here, okay, the electron lives in a sphere around that nucleus, right? So one electron, it could be here, it could be here, it could be here, but it can't leave this sphere. It's allowed to be inside, it's not allowed to be anywhere else. So when L equals 0, we get an s orbital, which looks like a sphere. Okay. Now when L equals 1, which again is one of the allowed quantum numbers that we saw, right? What we get instead is a p orbital. Right? A p orbital. So again, we need to start making the connection. The number to the letter, when L equals 1, we have a p orbital. In our slideshow for chapter 6 and 7, you'll see what p orbitals look like in slide number 4. P orbitals, right? When your electron has an L equals 1, it actually doesn't exist in a sphere around the nucleus anymore, right? And it exists in these shapes that kind of look like dumbbells, right? There's a big part above the nucleus, right? And a big part below the nucleus. And kind of view these as like regions, like I said, where you can live. Now these are three-dimensional, okay? So I'm just going to try to draw that here. Right? We say a dumbbell shape because it looks like, okay, something on the top, something skinny, and then something at the bottom. Okay, so hopefully you can kind of see that dumbbell shape. Right. What you'll notice on this slideshow is actually they show up in sets of 3. So there's one that looks like this, there's one that's oriented this way, and there's one that's oriented coming out and going away, right? But in general, what you see is this. Now, just to describe the strange behavior of electrons even more, what does this tell you? This tells you that sometimes the electron is up here, sometimes the electron is down here. It's never in the middle, okay? So somehow magically, and this doesn't make any sense to us, right? But this is quantum mechanics. Somehow magically, you'll find the electron here sometimes. Find the electron here a little bit less, right? The size of the lobe tells you, right, where you find the electron more or less, right? And then sometimes we'll find it here, but we never find it in the middle. So it's never in between the up and bottom lobe, right? The top and bottom lobe. But sometimes it's here and sometimes it's there. So how does it do that? How does it get from here to here? Quantum mechanics. And literally that has to be the answer at this level of science. And just got to say, hey, we're going to trust that it's the case, right? And just roll with it because the physics of small things is so different from our real world experiences that we just have to trust the math. Okay? The last L that we really focus in on, right? L equals 0, s orbital. L equals 1, p orbital. Looks like these dumbbell shapes. The last L that we really have to focus in on this semester is L equals 2. Because that's enough to get through most of the periodic table that we've cared about this semester, right? And when L equals 2, we call that a d orbital, right? And this is going to be on slide, or the set of d orbitals. And these are complicated. They show up in sets of 5. These are actually on slide 5, right? Slide 5. They show up in sets of 5, and in general, they have this clover shape. So again, if the nucleus is here, and there's one that looks a little different. You don't need to know these shapes in too much detail this semester. At the beginning of next semester, you kind of focus in on the shapes more and why they matter, okay? But it's good to know that they show up in set of 5. 4 of them look like a clover, and then the clover is oriented in different ways. And then one of them looks like a p orbital, but with like this donut in the middle, okay? Now think about what these shapes mean. Sometimes the electron's here, sometimes the electron's here, it's never in the middle, right? Sometimes it's here, here, never in these regions in between. Sometimes the electron's in the donut, sometimes it's in the upper lobe, bottom lobe. Where you don't see any shape, where you don't see any shading, you'll never find the electron. Right? So when L equals 2, we translate that into a d orbital. So why does an s orbital show up as one shape, a p orbital show up as 3 shapes, and a d orbital show up as 5 shapes? Right? That is all based off of the next quantum number, right? Which is our third quantum number, right? And this is m sub L, right? M sub L, right, is known as the azimuthal quantum number. And again, there's some mathematical reasons why we call that the azimuthal quantum number, okay? That's not important for us this semester. What the real world implication of the azimuthal quantum number is it gives the number of orbitals, right? Gives the number of orbitals for a set L, so for an L. It gives the number of orbitals for a given L, or for an L, right? So each m sub L is a different orientation. So different m sub L equals different orientation. So if there's a different orientation, then there's a different shape, right, of that set that's pointed in a different direction, right? And this 1, 3, 5, you'll see it all manifests, all right, from this quantum number rule. S orbitals are 1. P orbitals show up as sets of 3, each with a different m sub L, so each with a different orientation. D orbitals show up as a set of 5, each with a different m sub L and a different orientation. This all comes from understanding the quantum number rule for m sub L. And m sub L depends on L. Okay. All right. The values of m sub L are allowed. All right. Range. Okay, it's important. Ranged as integers from negative L through 0 all the way to positive L. Okay. So this dot 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 means you keep adding 1 until you get to 0, and then you go from there and you keep adding 1 until you get to positive L. So that's why it's m sub L, all right? We need to know L before we decide how many m sub L's are allowed. So let's look at those 3 cases that we just looked at for L. If we have an L equals 0, we know that that's an s orbital. Well, what m sub L's are allowed? Well, by this rule, what I do is I take negative L, which is negative 0, and then I count all the way up through 0 to positive L, which is 0. Well, hold on a second. This is way more complicated than it needs to be. What's negative 0? Negative 0 is 0, right? So hold on a second, right? If L equals 0, the only m sub L that's allowed is 0. The only allowed orientation you get is a 0 orientation. Now, whatever that means that when we have an s orbital, there's 1 m sub L that's allowed. So when I have an s orbital, there's 1 shape. Just that 1 sphere. Okay? What about when I have an L equals 1? Well, when L equals 1, we call that a p orbital. Right? Remember these showed up in sets of 3? Well, let's see why now. What m sub L's are allowed? Because each m sub L is a different orientation of that 1 shape. What m sub L's are allowed? Well, L equals 1. So I go negative L, right? This means I keep adding 1 until I get 0. Well, negative 1 plus 1 is 0. And then I stop once I get to positive, all right, L, which will be 1. So now we see why this gives us the number of orbitals, okay? How many m sub L's do we see? I see 1, 2, 3 different m sub L's. So when I have a p orbital, all right, I actually have a set of 3 p orbitals, right? One that's up, one that's doing this, and one that's coming out and going away. And you can kind of see this on the slideshow that showed the pictures of p orbitals. So even though it's not exactly the case, the way that you can view this is, right, this p orbital that's up and down, let's say that that's our negative 1 m sub L. This p orbital that's coming out and going away, this is our 0. And this p orbital that's in the plane but kind of making an X with the one that's up and down, let's say that that's our 1 orbital. So now you can see each orientation has a different m sub l. So the m sub l is controlling how many orbitals you see, right? The loud number tells you the number that you see. And so then finally, we'll have L equals 2. And when L equals 2, we have a d orbital. And for a d orbital, we have m sub l that equals -2, -1, 0, 1, and 2. And how did I get that range of m sub l's? Well, what does this rule tell me? Take my L, make it negative, put it here. Take my L, make it positive, put it here. Link up by adding 1, everything in between. So when we have a d orbital, right, we have 1, 2, 3, 4, 5 different m sub l's. So we have 5 different shapes, right? Now, even though we don't talk about them this semester, right, I do want to mention, just to practice the rule, there are f orbitals, right? What are the allowed values of m sub l when we have an f orbital? For an f orbital, we have L equals 3, okay? So try to do this quick in your notes. If I have L equals 3, what m sub l's are allowed? And then how many f orbitals show up? So like s orbitals show up as a set of 1, p orbitals show up as a set of 3, d orbitals show up as a set of 5. F orbitals show up as a set of what, right? So hopefully you're able to do that. -3, -2, -1, 0, 1, 2, 3, right? Those are the ranges, those are the values allowed, right, for m sub l given an L equals 3. So it shows up as a set of 1, 2, 3, 4, 5, 6, 7. Each one of these is an f orbital shape, whatever that is, and you don't need to know it. I'm just giving this as an example. Each one of these is a different orientation of that same shape. Okay. So now, the last quantum number is actually the easiest because it's off by itself. There's only 2 values that are ever allowed. The thing that's hard about this quantum number is what it actually means. And it's one of these things where you just have to kind of, accept it for what it is. Right? And our 4th quantum number is m sub s. And this is our spin quantum number. Now, spin is like an intrinsic angular momentum, which doesn't really mean much to us at this point in our scientific progression, okay? It's just a purely quantum mechanical property. And it really matters for electrons because m sub s, it doesn't depend on any of the other quantum numbers. M sub s can only have 2 values, right? It can either be +1/2 or -1/2, and that's it. So what we say is, right, this intrinsic property, whatever it means, it's not really that the electron is spinning, it's just spin is like the closest real world analog to what it does. So you can kind of think about it that way if you want to, because it doesn't really harm you in any way to think about it that way. But it's really just this mathematical quantity that amounts to understanding the behavior of electrons when they're near each other. And so when we have an m sub s that's +1/2, what we say is that the electron is spin up. And we'll have these orbitals that will draw as lines, kind of like in our energy level diagram we had before. And the way that we're going to represent an up is with a half arrow up, okay? This translates into an m sub s, right? That's +1/2. When we have an m sub s that's -1/2, what we say is that its spin is down, okay? So if I look at placing it in an energy level diagram, right, what we'll do is we'll do a half arrow pointed down, okay? And that's all we really need to know about spin. It's not linked to the other quantum numbers, okay? It is kind of this weird thing that we have no real world analog to, but the closest thing is spinning. And so the way that we view it is an m sub s could be +1/2. We call that spin up. We draw a half arrow up representing the electron's behavior. And the m sub s could be -1/2 and we say it's spin down and we draw a half arrow down, okay? So these are the 4 sets of quantum numbers that I have to realize or worry about, okay? So these are the 4 quantum numbers that we care about for electrons. We have to know what they describe. We have to know the rules. We have to know how they interrelate. And we have to know like what sort of information we get from them. Okay? So please try to, focus in on not just answering questions from homework, like, okay, if I give you an N, what are the L's allowed, right? But try to link together what you can about what they physically describe about the electron. The electron is quantized in a lot of its properties. Some things are allowed, some things are forbidden, okay? Now what we're going to do next time is we're going to mesh all this with the periodic table. All these quantum numbers are hidden on the periodic table. And the structure of the periodic table that we see is all based off of understanding these quantum numbers and the rules associated with them. So that's the linking that we're going to do next time.